Newtonian Mechanics. This is Chapter 1, Physics and Measurement. I'm Dr. Golben. Let's start with a quote from Galileo Galilei, scientist so important that they had to repeat his name twice. Philosophy is written in that great book which ever lies before our gaze, I mean the universe, but we cannot understand it if we do not first learn the language and grasp the symbols in which it is written. It goes on to say, the book is written in the mathematical language, and the symbols are triangles, circles, and other geometrical figures, without the help of which it is impossible to conceive a single word of it, and without which one wanders in vain through a dark labyrinth. Very interesting quote. What is he trying to say here? He's trying to explain really the whole idea behind science and physics, and that, for that matter, the idea to try to understand the natural world around us, and your tools are mathematics and analytical reasoning. Now, in Galileo's time, the mathematics extent was geometrical figures like triangles and circles and things like that. Today, it would be the very cutting edge of mathematics. It would be differential equations, tensors, calculus. That, even beyond that, would be the limits of the mathematics that we could use to describe our world. But underneath it all is trying to understand nature and seeing that there is a logical basis to it all. It's really quite interesting. So wow, the book of nature is written in mathematical characters. So what do we mean by physics? Physics is a foundation on which other physical sciences are based. We have mechanics, which will be the basis of this course. Newtonian Mechanics, which will go back 350 years to the time of Newton. Thermodynamics, the study of heat exchange. Sound and waves, the study of sound. Sound is a wave, and by studying waves we can understand sound better. Light is a wave as well, so understanding wave properties is very important. We'll look at that in physics too. Electromagnetism. Electrodynamics is the study of electric charges and their effects. Magnetism is the study of magnetic fields. They're actually interrelated. If you change one, if you change an electric field, you get a magnetic field. And if you change a magnetic field, you get an electric field. So they're interrelated. The source of magnetism on a very small scale is charges moving around the atoms. So electric charges moving and changing the electric field creates the initial source of magnetism. So we'll study that in physics too as well. Optics is the study of light. Light is an electromagnetic wave, and that's something that we would study in physics 3. Relativity is a study of things that can move very fast, and as a result, the observer's reference frame can change. It's based on two postulates. One is that the laws of physics are the same in all reference frames, and the other one is that the speed of light is a constant, 3 times 10 to the 8 meters per second. Based on relativity and based on these just two simple concepts, two simple objectives, it comes up with some very strange ideas that time could be different for different observers. We could travel 4 light years away to Alpha Centauri, our nearest star, and from an observer on Earth, if you traveled at the speed of light, it would take you 4 years to get there at the speed of light and 4 years to come back. So traveling at the fastest speed possible, an observer on Earth would record that it took you 8 years to get there. But if you travel near the speed of light, time would slow down in your reference frame, and it's possible you could get here from Alpha Centauri in a matter of minutes or hours, and turn around, come right back, and age just a few hours in your time, while people on Earth aged 8 years. So it's a rather bizarre concept, but based on all the data results recorded so far, it pretty much supports the theory of relativity. It's a theory, but theories in science are very strong. If you prove a theory wrong in science, you have to throw it out, or you have to modify it to account for your observations that might throw it out. So you have to modify the theory to include any exceptions. But the relativity, so far no one has proven it wrong, and there's a lot of data points to prove it right. Quantum mechanics is a study of things that are really small, like on the order of an atom. If you get down to that order, it's hard to actually make measurements because of the probabilistic nature of the location of particles. So you pretty much would have to say, there's 40% of it possibility that's found over here, 60% possibility is found over here, and we have to work with that. It's another theory, but if we throw this theory out, then we might as well throw our iPhones and computers and other electronic devices out too, because a lot of their principles are based on the ideas of quantum mechanics, or else we have to find a better theory to cover these things, and right now we don't have that. Physics, history, and evolution. Recent revolutions. Galileo developed the scientific method. The scientific method is based on making observations, coming up with hypotheses as to why these observations take place, conducting controlled experiments to test these hypotheses, and then coming up with results. You publish your results. Everybody around the world can look at them, and they can try to repeat your experiment based on what you've said. And if everybody in the world, or anybody who's been looking at this, agrees with you, and if everybody agrees, then you can take one little step on the staircase of knowledge, one little scientific steps of facts. If somebody doesn't agree with you, if somebody runs your experiment, comes up with different results or different conclusions, then you have to talk it out and figure out what's gone wrong and why you have different conclusions. Eventually, everybody has to agree before you take that step. And Galileo came up with this scientific method about 400 years ago, and it's allowed us to advance in technology since then. Kepler made mathematical calculations based on the astronomical data of Tycho Brahe, and based on those astronomical calculations, he was able to determine the nature of planetary motion. So why planets move in ellipses, why they move faster when they move closer to the sun and slower when they're further away, and a relationship between their time period around the sun and their distance from the sun. Based on this mathematical calculations, Newton was able to prove his laws of motion and his law of gravity. So he had the data and the calculations and the theories of Kepler in order to prove his theories of motion and gravity. So it was very essential that he had that. We call all of this classical mechanics, and it'll be sort of the nature of this course, Physics 1, is to focus on mechanics, the same mechanics that Newton used 350 years ago. So we could use any book over the last 350 years that dealt with mechanics to cover this subject matter if we wished. More recently, Einstein, in the last 100 years, Einstein came up with the theory of relativity, which I touched on just a moment ago. Madame Curie studied radioactivity, and I believe she's the only scientist to have won the Nobel Prize in 2 different scientific disciplines. She won it in chemistry and physics. And she died for her efforts because no one really knew about the ill effects of radioactivity back then, and she died of the effects of radioactivity. Many others in the modern era contribute to this modern physics of the last 100 years or so. In this course, we are going to focus on the System International unit system, SI system, otherwise known as the metric system. In this metric system, a standard unit is a fixed and reproducible value for the purpose of taking accurate measurements. The System International Unit System has 7 basic units. The second, a measurement of time. The meter, a measurement of distance. The kilogram is the measurement of mass. And there's 4 others. There's the ampere, a measurement of current. Kelvin, a measurement of temperature. Candela is a measurement of brightness. And the mole, which is the mole. Now the mole is a measurement of number, and we can see that the mole creature is actually well suited for the measurement of number because he has quite a lot of whiskers, which you can count, or a lot of claws in order to count with. So basically a mole is a measurement of number. We are going to focus on 3 of these in particular: the second, the meter, and the kilogram. We can also have a derived unit based on these 3 in particular, and so a derived unit is a multiple or combination of these units, and they're used so often that you come up with another name for that new unit. So like a Newton, a unit of force, is a kilogram meter per second squared. And so instead of saying kilogram meter per second squared, we just say newtons, unit of force. In the metric system, the System International Unit System, we are focused on powers of 10. And here are some powers of 10 that you should know. 10 to the minus 9, which would be 1/billionth of something, is a nano. So if you talk about nanometers or on the nanoscale, then you're talking about 1/billionth of a meter on that scale. Micro is 10 to the minus 6. Milli is 10 to the minus 3. Centi is 10 to the minus 2. Deci is 10 to the minus 1. Kilo or kilo is 10 to the 3. It's 1,000 of something. Either 1 kilo or kilo is correct. Mega is 1,000,000 of something, 10 to the 6. And giga is 1,000,000,000 of something, 10 to the 9. Kind of goes in many times in ratios of 3 on these powers of 10. If you were to go higher, 10 to the 12 would be a tera, would be 1 trillion of something. 10 to the minus 12 would be 1 pico of something. And so these are good prefixes to know. I'm going to require that you know them. Everything in this first chapter are things that you should know going into this course. Time. The continuous forward flowing of events is time. How do we measure that? Well, we use in units the second. And how did the second usually come about, or originally come about? Most likely it was someone's heartbeat. A heartbeat is very close to being a second, and so maybe the original unit of time, the second, came from somebody's heartbeat. This is not good enough for science, at least in the modern day. So in 1900, the second was redefined as 1/86,400th of a mean solar day. I don't know why they didn't choose a nice solar day as opposed to a mean solar day. That's just the way they were back then. This is still not good enough for science today. So currently the second is redefined as 9,192,631,770 periods of cesium-133 radiation. Much better. So you have a radiation that is periodic and has a definite frequency, and if you take that many periods of it, you can define the second. Under this definition, there are approximately pi times 10 to the 7 seconds in a year. If you took 365.25 days, 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute, multiplied all that out, you would get 3.16 times 10 to the 7 seconds. So saying there's about pi times 10 to the 7 seconds is a good way to remember that, and that should be a rule of thumb you probably want to memorize. Here is a picture of an atomic clock, which is producing that cesium-133 radiation. Length. In 1799 AD, the distance from the North Pole to the equator was defined to be 10 million meters. Here's how it might look. We have the Earth here, and if we went from the North Pole down to the equator, we would have 10 million meters. And hence, by definition, that pretty much sets the circumference of the Earth to be 40 million meters. Because if you went from the North Pole to the equator, that's 10 million meters. The equator to the South Pole would be another 10 million meters. South Pole back to the equator would be 10 million meters. And then the equator back up to the North Pole, 10 million meters. So 40 million meters all the way around the Earth. If you measured it around the equator, very close to 40 million meters. Because the Earth's spinning, it bulges a little bit at the equator, and so the equator is a little bit more than 40 million meters, but it's 40 million point 00 something. So it's very close, by definition, to 40 million meters. This is not good enough for modern science, so science redefines the meter, and the meter is the distance light travels in 1,299,792,458th of a second. This is actually quite beautiful because you take the speed of light, which is a universal constant. No one's proven that anything can travel faster than the speed of light in a vacuum yet. So you take a universal constant and you say, and you take your time, which you've already defined, you take your time of 1 second, and you say in 1,299,792,458th of a second, that's how long our distance of measurement, a meter, is. That was beautiful, because you take something that's pure, like the speed of light, something you've already defined, and now you redefine the meter. Love it. Originally, the yard was defined as the distance from the King of England's nose to the end of his hand in 1120 AD, now defined exactly as 0.9144 meters, and the inch is exactly 2.54 centimeters. I have myself a meter stick here, which is 3 inches longer than a yard. So I want to do this. And if I go back like this, I stretch out here, I probably stretch to within about 3 inches of the end of this meter stick. And maybe originally the meter was from the King of France's nose to the end of his hand, which probably was the original definition of the meter, which is about 3 inches longer. The foot was originally defined as the length of Louis XIV's foot. All this was not very good because if you're in the marketplace and you needed 30 meters of yarn, you would have to ask the king to come out there and measure out 30 meters of yarn from the tip of his nose to the end of his hand, and he had better things to do than probably going out there and measuring yarn for you. So you had to have a standard measurement that everyone could use, and that's what we have now. Mass. A gram of substance in terms of mass is defined as 1 cubic centimeter of pure water at 4 degrees Celsius. This is also beautiful because we just defined the length based on the second and the speed of light. And now we're defining the mass of something based on water. Water is a substance that needs to be wherever we are, because wherever we go, we need water. We are 95% water ourselves, and so for us to survive, water better be there. So if we go to the end of the universe, water better be there. So we're defining mass based on a substance that's going to be with us wherever we go. 1 cubic centimeter of pure water is a gram. We measure it at 4 degrees Celsius. Why 4 degrees Celsius? I know you're answering on the other side of that camera. Well, 4 degrees Celsius because water gets denser and denser. Like most liquids get denser and denser as you solidify them and as you cool them down. So water gets denser and denser as you cool it down towards 4 degrees Celsius. And then a strange thing happens at 4 degrees Celsius. Water being a polar molecule, as you continue to cool it down from 4 degrees Celsius to 0 degrees Celsius, the polarity of that molecule starts expanding the structure as you get some repulsion, and starts forming a structure as it forms a solid. And hence the solid of water is less dense than it is at 4 degrees Celsius. And hence ice will float instead of sinking to the bottom of the liquid. This is a very unusual property of water. It's not true of most liquids. And it's a good property because it allows life as we know it to exist. If ice were to form at the bottom of lakes and the bottom of the ocean, then creatures that would live underneath the water would die. It's good that ice forms on the top, actually forming an insulating layer so that life can go on underneath that layer in wintry climates. The kilogram is actually the unit that we use in the SI system. It's 1,000 grams, and it's the only metric SI unit that has a prefix in front. So this is the only one that actually uses a prefix as the basic unit. The kilogram is the basic unit of mass in the SI system. 1 liter of pure water, which would be 1,000 cubic centimeters of water, is 1 kilogram. So if you had a liter of water, which I do not, but if you carried around a liter of water, you would have 1 kilogram of water, which translates to about 2.2 pounds on Earth. If you're under the gravity of Earth, 2.2 pounds. Here is a picture of the standard kilogram mass at the Bureau of Standards, and it's made of platinum iridium, and it's a cylinder. And it's chosen a platinum iridium not just because it's expensive, but because that material does not oxidize very easily. So you could have that material out in the open and it would not really oxidize very well. But even so, it is encased in a bell jar, which has a vacuum. So it's evacuated so that there's no air or oxygen to even attack the platinum iridium. It's under a bell jar. And even that's not good enough. They have a second bell jar also evacuated. So you have an evacuated bell jar, another bell jar. You have this material that does not react very well. And even so, the standard kilogram under this does change mass over time. So it's good to have just a standard based on the cubic centimeter of water at 4 degrees Celsius, because that's a standard that won't change. Checks. As we go through this course, we want to use checks. We use dimensional analysis to check our equations. An equation is only correct in terms of structure if the dimensions of one side of the equation are equal to the dimensions on the other side of the equation. For instance, let's say you had an equation, distance equals speed times time. So you might say, all right, distance is measured in miles. My speed might be miles per hour. And if I multiply that by hours, the hours will cancel out. And I'll have miles is equal to miles. So at least in terms of dimensions, this equation is correct. Miles equals miles. I know that in terms of structure, I've got the right kind of equation to work. Order of magnitude calculations. I might use order of magnitude calculations to help make a guesstimate and check my answer just to make sure that it makes sense. For instance, let's say someone asked you, what is the distance from the Earth to the Sun? And you happen to know that the speed of light is 186,000 miles per second. And it takes approximately 8 minutes for the light from the Sun to reach the Earth. So if you use this idea that distance equals speed times time, use the speed of light and the time it took to cover that distance, you could get pretty accurately the distance from the Earth to the Sun. But this might not be a very good calculation to do in your head, so you do a little bit of rounding, and you'll say 186,000 miles per second is approximately 200,000 miles per second, just rounding up. And 8 minutes, which is 480 seconds, that's approximately 500 seconds. So I have 200,000 times 500 seconds would give me about 100 million miles. So I would say approximately 100 million miles from the Earth to the Sun. Actual distance is 93 million miles from the Earth to the Sun. So if you made this guesstimate and you actually made the calculation, you would find that it actually made pretty good sense. This, incidentally, was the first $100 million question on Who Wants to Be a Millionaire. So if you were on the show Who Wants to Be a Millionaire, knowing physics could have won you some money, would have won you $1 million. Or if you didn't think of the answer right away, you could call me, phone a friend. I would give you the answer, and we'd split the money, $50 million each. That's fine with me, if it's fine with you. Significant figures. When multiplying or dividing several quantities, the number of sig figs in the final answer is the same as the number of sig figs in the least accurate of the component quantities. Here's 3 numbers that we're producing in a product. First number, 45.678, has 5 significant digits. The second number, 5.1, has only 2 significant digits. The third number, even though it has a 0 out front, has only 3 significant digits. The 0 is just a place, allowing us to write the number 0.104. If I were to multiply these 3 numbers, I would come up with a number, an answer, but then I would have to round it up to a point where I only had 2 digits in my answer, because the least significant, least accurate of the component quantities, the 5.1, only has 2 significant digits. If I were to add 3 numbers together, they are only accurate to the least significant place in the addition. Here I have 45.678. It's accurate out to the thousandths place. 5.1 is only accurate out to the tenths place. 0.104 is accurate to the thousandths place. But since I added these together, I would just go ahead and add them all together. And then I'd have to round up to the least accurate place, which would be the tenths place. So my final addition number would be 50.9 for the addition of these 3 numbers. Zeros are used to position the decimal place. They may or may not be significant. Those after other digits may or may not be significant as well. Here's an example. Here are 3 numbers, a product again. Now our middle number has 3 significant digits because we added a 0. It's now significant out to 3 numbers together, like these 3 numbers, all of them accurate out to the thousandths place. My answer is accurate out to the thousandths place as far as the addition of these 3 numbers. That's how you do significant digits. For the purposes of this course, I would ask that you maintain 3 significant digits on all your answers. If your calculator gives you 10 significant digits or 10 digits, don't write 10 digits out. Just round everything to 3. Even if I give you only 1 significant digit, just round everything to 3, and we'll maintain ourselves that way. I'm not going to be a stickler for that, but I don't want excessive digits and I don't want too few digits. So let's just keep it at 3 significant digits, scientific notation, in our answer. Trigonometry. Here's a triangle, a right triangle. It's got 3 sides and an internal angle theta. By a right triangle, it's got a 90-degree angle between side A and B. By definition, for the angle theta, we say that the sine of theta is the length of the opposite side over the length of the longest side of this right triangle, the hypotenuse. So it's the length of A divided by C, by definition. By definition, we define the cosine of angle theta as the length of the adjacent side to that angle, B in this case, to that longest side, hypotenuse C. By definition, the tangent is the opposite side A divided by the adjacent side B. So these are all definitions in trigonometry. We can use these definitions. If I take this first equation and multiply it by C on both sides of the equation, I would get that the length A is equal to C times the sine of theta. Looking at the second equation, if I multiply both sides of the equals by C, I would get that the length B is equal to C times the cosine of theta. And if I look at this third equation, take the inverse tangent of both sides, I would get that the angle theta is equal to the inverse tangent of length A divided by B. So these are things I want to do with this situation. Finally, I would recognize the Pythagorean theorem. I would say that A squared plus B squared equals C squared for this right triangle. Hence, C is equal to the square root of A squared plus B squared. By the Pythagorean theorem, and these are essential data. This is the essential information that you need from trigonometry for this course. That's a course in trigonometry in one screen in just a couple minutes. Now you don't have to take a course on that. You've got it right here in one screen in this course. Here are two common right triangles, useful. The 3, 4, 5 triangle comes up quite a lot in this course and in other courses. It has internal angles of 36.9 degrees and 53.1 degrees, and has ratio sides of 3 to 4 to 5. This can come up when you least expect it. Sometimes you might have a problem like in chapter 4 where you're shooting projectiles, and the problem they might say, a projectile is shot at an angle of 36.9 degrees at 20 meters per second. And you're thinking, physics is tough enough. Why don't they give us just a nice angle like 30 or 40 or 50 degrees? Why don't they give us an angle of 36.9 degrees to shoot the projectile with? Why don't they make it more harder than it should be? And the answer is they're actually trying to make the problem easier. By shooting the projectile at 36.9 degrees, 20 meters per second, you actually have a ratio of 3 to 4 to 5. So you know that your horizontal speed is 16 meters per second and your vertical speed is 12 meters per second while you're shooting it at 20 meters per second at 36.9 degree angle. So they're using the 3, 4, 5 triangle to try to make that problem easier as far as finding your component velocities. So watch out for that. Here's another triangle, very useful, the 30-60 triangle. In this triangle, the side length opposite the 30-degree angle is 1/2 the length of the hypotenuse. So the sine of 30 degrees is 0.5. And the cosine is 0.866. Comes up quite a lot. Two common trigonometry laws. Here's just a basic triangle, not a right triangle, just any arbitrary triangle. It's got side lengths A, B, and C, and internal angles alpha, beta, and gamma. Alpha opposite the side length A, beta opposite the side length B, and gamma opposite the side length C. For this arbitrary triangle, we have two laws. There's a law of sines, which says that the ratio of A to the sine of alpha is equal to B divided by the sine of beta is equal to C divided by the sine of gamma. So these are the ratios of sides to the sines of the angles, and this could be quite useful in trying to determine the lengths of arbitrary sides on an arbitrary triangle like this. We also have the law of cosines, which says that C squared is equal to A squared plus B squared minus 2 times AB cosine gamma if we're talking about the gamma between sides A and B. This is the same as the Pythagorean theorem if gamma is equal to 90 degrees, because the cosine of 90 is 0, and that third term would be gone, and you'd simply have C squared equals A squared plus B squared. But if you don't have a 90 degree angle, if you have just some kind of arbitrary angle gamma, then this is how you would solve that kind of situation with the law of cosines. So these can be very useful, especially when we get into vectors coming up later. Geometry. This is a rectangle, side length A and B. The area of this rectangle is A times B. Here's a parallelogram, side lengths A, B, and C. The volume of this parallelogram is A times B times C. So there's the area of one side, the rectangle, multiplied by the depth through the parallelogram, the length C. So I can think of that as area times C, or A times B times C. Here's a circle of radius r. The circumference of this circle, the perimeter length around this circle, the circumference, is equal to 2 times pi times r. Pi being an irrational number, 3.14159, blah, blah, blah. Never ends. So the circumference is equal to 2 times pi times r. The area of a circle is pi r squared. The surface area of a sphere is 4 pi r squared. And the volume of a sphere is 4/3 pi r cubed. These are things you should know going into this course. If you're reading a physics problem and they're talking about a ball or something like that, and maybe one of the things you need to know in order to solve the problem is the volume of a sphere, 4/3 pi r cubed. It's not going to be given to you in the problem. It's going to be assumed that you know this. So you should know this. You should memorize these formulas for circles and spheres. Just as an offshoot, the simplest technological device, one that helped humankind start to advance in technology, was the wheel. You use the wheel to transport materials more easily from place to place by a cart or something like that, and allowed human civilization to progress. So the simplest technological device in history is the round wheel. And you would say, well, we should know everything there possibly is to know about the wheel. But we can't know everything there possibly is to know about the wheel because, for instance, the perimeter of the wheel, measured by 2 pi r, is an irrational number. So you can't ever know exactly what the perimeter of a wheel is because it's irrational. It has no end. So you can never get an exact figure for the perimeter of a wheel. Likewise, for the area of the wheel as well, pi r squared. So there is some, even on the simplest device, there's some irrationality to it. Kind of interesting from a theological perspective, if you wish. Here's a cylinder. The volume of a cylinder is the cross-sectional area A multiplied by its depth. You can do that with anything that has a uniform cross-sectional area. So the area of a parallelogram, cross-sectional area A multiplied by its depth, H. The volume of a footprint would be the cross-sectional area of the foot multiplied by its depth would get you the volume of the footprint, which you could probably translate, depending on the springiness of the mud, into how much the creature weighed. And if you could determine that, you could possibly determine whether this footprint was made by somebody playing a trick on you or whether it was actually made by Bigfoot himself. So that would be a good thing to be able to determine. This chapter, this chapter 1 in physics, is really just a summary of the mathematics that you should know going into this course. There's really not a whole lot of physics in this chapter. It's really mainly just reaffirming your mathematics. So you want to study this chapter, get good at it, but the real physics begins in chapter 2. So let's go there.